Hi students, now we are going to learn about alternator and synchronous motor. So alternator is the machine which produces three-phase power from the mechanical power, that is alternator, and it works on the principle of electromagnetic induction. Okay, as usual alternator is also having stator and rotor. Armature winding is mounted on stator and field winding is mounted on rotor. Okay, and the field magnets are magnetized by three-phase supply through the slip rings. Okay, and also these field windings are connected with alternate north and south poles. Okay, then so as the rotor, when the supply is given, the rotor rotates and the armature conductors cut by the magnetic flux, so the EMF will be induced in an armature conductors. Okay, and here the frequency of this induced EMF depends on the number of poles and the speed of the rotor. Okay, therefore F is equal to Pn by 120. N is the speed of rotor and P is the number of rotor poles. Okay, now we will see the equation of an induced EMF. We all know the induced EMF is directly proportional to d phi by dt. So here for one revolution of the rotor, each stator conductor is cut by a flux of 5p Webers. Okay, therefore d phi is equal to 5p and dt is equal to 60 by n seconds. Okay, now you can substitute these values in d phi by dt. Therefore we will get average EMF induced per conductor that is equal to d phi by dt. What is the value of d phi? D phi is 5p and the value of dt is 60 by n, that is equal to 5pn divided by 60. Okay, and we know F is equal to, the frequency depends on number of poles and the speed of the rotor, therefore F is equal to Pn by 120. Okay, and here N is equal to 120 F by P. Okay, from this we will get N is equal to 120 F by P, and substitute the value of N in this EMF induced per conductor. Therefore average EMF per conductor is equal to 5p by 60. Instead of n, you have to substitute 120 F by P. Therefore you will get the answer as 25 F volt. So the average EMF per conductor is 25 F volt. Okay, so this is for per conductor. If there are Z conductors per phase, therefore average EMF per phase is equal to 25 F into Z volt. Okay, so substitute Z is equal to 2 into T, that is T will be the number of turns or coils per phase. Therefore average EMF per phase is equal to E equal to 4-5 F into T. Instead of Z we substitute the value 2T, so we will get 4-5 Ft volt. So therefore RMS value of EMF per phase is equal to 1.11 into this value. So therefore RMS value of EMF is 4.445 Ft volts. That's all about alternator. Okay, so alternator is nothing but it is a three-phase power which produce three-phase power from mechanical power, right? It works on the principle of electromagnetic induction. Then as usual you are having stator and rotor. In stator armature winding, in rotor you will be having field winding, right? So the field magnets are magnetized by supply through slip rings. Okay, and field windings are connected with alternate N and S poles. So here when the rotor rotates, armature conductors are cut by the magnetic flux, so hence an EMF is induced, right? And frequency will depend on number of poles and the speed of the rotor, right? So next you have to find the EMF equation of the this alternator. Okay, next topic is synchronous motor. Next we will see about synchronous motor. So here synchronous motor, this is synchronous motor. So synchronous motor, it is a type of 3-phase AC motors. Okay, it is a AC motor which runs at a constant speed. So it runs at a constant speed and it converts electrical energy to mechanical energy. That is synchronous motor. Mainly it runs at a constant speed. And also it is a self-excited motor. We don't want to give any external force to excite this motor. So it is a self-excited motor. And here as usual, synchronous motor also having stator and rotor. Okay. And here this motor is excited by the 3-phase AC supply. So here this motor is excited by the 3-phase AC supply. And stator is having armature winding, rotor is having field winding. Okay, rotor is excited by, stator is excited by 3-phase AC supply and rotor is excited by 3-phase DC supply. Okay, and so here in synchronous motor, when AC supply is given to stator winding, it generates magnetic field. Okay, it generates magnetic field rotating at a speed known as synchronous speed. So synchronous speed of the synchronous motor is Ns is equal to 120 F by P. That is, it depends on the frequency and the number of poles. Okay, so therefore the synchronous speed is Ns equal to 120 F by P. And this synchronous motor is not a self-starting motor. Okay, so here as usual we are having stator and rotor. Stator is having magnetic poles and rotor is also having magnetic poles by their own. So here stator poles Ns and Ss will be assumed to rotate in clockwise direction at a particular synchronous speed, that is Ns is equal to 120 F by P. Okay, and the rotor poles are formed by the DC excitation. As I said, rotor is excited by DC supply. So these rotor poles are formed by the DC excitation which rotates in anti-clockwise direction. So by this two poles are repel each other. Okay, so after a half cycle later, the stator poles and rotor moves in same direction, and these stator poles and rotor poles gets attracted and rotor tries to rotate in clockwise direction. So this implies rotor experiences a torque in different directions every half cycle. Every half cycle rotor experiences a torque in different directions. So this has no starting torque. Okay, so now we are going to see the torque equation of the synchronous motor. So here the applied voltage V is the vector sum of the reversed back EMF and the impedance drop, that is IA into current is IA, and by adding RA XS we consider ZS. So therefore V is equal to reversed back EMF is V is equal to minus EB plus IA ZS. Okay, so now we will find the torque equation of the synchronous motor. Consider this phasor diagram of synchronous motor. From phasor diagram you have to find the sine alpha. So here this is angle alpha. So from the sine alpha is equal to opposite side by, we all know opposite side by hypotenuse, right? So here opposite side is this. So similar to this value is AB. Therefore sine alpha is equal to AB by hypotenuse is back EMF, so EB. Okay, from this rearrange and write the value of AB. AB is equal to EB into sine alpha. Consider this as equation 1. Similarly, you have to consider cos phi. So this is, consider this angle cos phi. Cos phi means adjacent side by hypotenuse, right? So this is adjacent side AB, then hypotenuse. This is hypotenuse value. So hypotenuse value here is IA XS. Therefore cos phi is equal to AB by IA into XS. Okay. So from this AB is equal to IA excess cos phi. Consider this as equation 2 and equate these two equations 1 and 2. Therefore EB sin alpha is equal to IA excess cos phi. From this bring excess to left hand side. Therefore EB sin alpha by excess is equal to IA cos phi. Okay, we all know P is equal to V into I cos phi, right? So here by this equation we can consider P is equal to V into IA cos phi. What is the value of IA cos phi? EB sin alpha by excess. So instead of IA cos phi, substitute P is equal to V into, instead of IA cos phi you can write EB sin alpha by excess. Okay, that is the power of synchronous motor. So for 3-phase power you have to multiply it by 3. Therefore PM is equal to 3 into VEB by excess sin alpha. And now the torque developed by the motor, that is T is equal to this PM divided by WM. The value of WM is 2 pi n divided by 60. Okay, now you can substitute the value of WM, that is 2 pi n by 60. By substituting you will get the torque value T is equal to 60 by 2 pi n into PM. From this you will get the value T is equal to 9.55 PM by n. Okay. Sometimes you will get a question to find the torque value of the synchronous motor. You can use this formula. Okay, that's all about synchronous motor. So synchronous motor is nothing but it is a AC motor which runs at the constant speed, right? It converts electrical energy into mechanical energy, and the important point is it is a self-excited motor. We don't want to give any external force. Okay, so constant speed motor. It is the constant speed motor. As usual, synchronous motor is also having stator and rotor. So stator is excited by 3-phase AC supply and rotor is excited by DC, 3-phase DC supply. So armature winding is in stator and field winding is in rotor. Okay, and it is not a self-starting motor. Okay, so it does not produce any self-starting, it has no starting torque. Okay, hope you all understand this video. Thank you.